Okay, recording starts. So, today we're looking into the so-called half-life. When we have some unstable nucleus, some element with unstable nucleus, they decay. And some decay faster, some decay slower. We cannot predict which particular nucleus will decay. But what we can measure how long it takes for certain material, radioactive material, so unstable material.
What should I label this page? Okay.
Today's topic is half-life.
Oh, okay.
Half-life. So, if we have some unstable material, for example, unstable nucleus, and let's say, for example, we have iodine 131, and we will look how it will decay. So we'll measure, we have certain number of the atoms of iodine, in this case 400, and we will measure how many, because what we can measure. Can we count how many have not decayed?
Yes.
How?
By looking at which ones decay.
How we can count the atoms? Very probably. But what we can count? How many decayed in a certain amount of time. Why? Because when something decaying, we have either alpha particle coming, either beta, or electron, or positron, and we can detect it. So counting how many acts of decay happen, we know how many decayed, we can calculate how many left. So let's consider we have 400 atoms and we start observing what's happening. And as you can see, red when undecayed, blue decayed. So as time going by, we have eventually, because it's only, we measure only 400 seconds, we have 7 left undecayed. And if you take the same material, and we will again measure how it will be decaying, we will get exactly same time, exactly same array of decay. So we cannot predict which nucleus will decay. It's a random process. What change? 6. Yeah, let's say it can be slight variation. Now, we cannot predict which one, but we can predict what percentage or what fraction will decay or left undecayed. And period of half-life is the time, how long, so half-life is a time. It's time how long it takes for half of the material decay. I will suggest to close laptops and pay some attention.
So the time it takes.
So half-life is a time, how long it takes for half of the nucleus that we have, half of the material to decay. Yes?
Why do we measure it by half, not by full?
Full, it might be never happen, or it might, because it's a random process. So full, when we divide it by 2, let's say we take 100, we divide by 2, 50, 25. Then divide by 2, we have either 12 or 13, because we cannot have 12 and a half atoms left. And let's say we have 13. then half of that, 6 or 7, let's say 7. Half of that, let's say 3. Half of that 1. So, but we don't know when the last one decays. So we can estimate realistically, usually, how long it takes for half of the material decay. So, let's say period of the, I will round the period of decay of the iodine 131. Iodine 131. What does number 131 means in this, when I write like this? Yeah, which?
Atomic mass.
This is atomic mass, yes. This is atomic mass. And it has period of half-life of 8.07 days. Will take 8 days to make calculations here. So we will use capital letter T to denote the period of half-life. So let's say it's equal 8 days. And if we have, let's say we have 100, to make it easier for calculations, let's say we have 1024 atoms of iodine 131. We know that half of them will decay in 8 days. So after one period of half-life, which is 8 days, how many will left undecayed?
6.
Half of them decay. We have 1024. 512. If half decay, how many left? 512, half of 1024. If we take now after 2 periods of half-life, so after 16 days, so another 8 days, half of what we have left decay. So we have 256. Then after 3 periods of half-life, so 24 days, again we have that half of this decay, we have 128 left. 4 periods of half-life, so 32 days. We have 64 left. 5 periods of half-life, so 40 days. We have 32 left. 6 periods, it's 48 days. We have 16 left. 7 period of half-life, 56 days. 8, then 4, 2, 1. 8, 9, 10, so 80 days. 80 days, 72 days, 64 days. So that's how it will be decaying over the time. How number of undecayed nucleus will be changing over the time. Each time, so every half-life is halved. Not the same number decay. Because here we have 512 decay. Here we have half of this, so not another 512 decay. Half of 512, so 256. So every period of half-life, a number of the undecayed atoms becomes half. Make sense? If you sketch the graph, how it will be changing, number of remaining undecayed atoms over the time, we will get time. This is a number of undecayed atoms. So we start from N0. And let's try for sketching the graph derive formula. How we can get formula. If we halve every time. How we can express it mathematically? So we have initial, so number that's left undecayed, n equal, we have initial number, how many we have at the beginning. So we need divide by 2, so we times 2 in negative to get after 1 half-life, we times 2 in negative 1. After 2 periods, times 2 in negative 2. The divided by 4 in negative t divided by the half-life. Because that is a number of how many half-lives pass. So we have 124, we have 512, that's 1 period of half-life pass. And so we times it by 2 negative 1. Then 256. It's 2 period of half-life, so we divided initial by 4, so we times by 2 in negative 2. Then 2 negative 3, and so on. So what is this? What the power is? How many half-lives pass? Number of half-lives. Does that make sense? So this power will be number of the half-lives. We have twice, divide by 4, then we have 128, we divide by 8, then divide again by 2, will be by 16, so that will be 2 in negative 4, and so on. Yes, you have a question?
Oh, no, I understand. Thank you.
So power is number of the half-lives. Yes?
The camera's not getting the full whiteboard. Do you want me to tilt it over a little bit?
Hmm?
Like there's a bit like out of it. On the like you weren't in the thing. Yeah, that's good. Okay.
Better watch out for the subscribers.
So we have every time we multiply, this is a number of half-lives. How we can calculate number of half-lives? We divide the time by the period of half-life. So if, let's say, we have period of half-life, we say 8 days. So time equal 32 days. How many periods of half-life that will be? 4. We divide 32 by 8. So this will be formula describing number of undecayed nucleons. And 0, how many we have at the beginning, times 2 in power negative t over half-life. Which is, this is t over t is number of half-life, of half-lives. And this graph will be who doing, at least who doing methods should know how we name this type of graph.
Exponential.
Exponential. This graph called exponential graph. So that's how it will look like over the time. That is exponential graph. So let's do the next example. If we have, for example, if we have, so make sense? So let's consider next example. If we have 500 grams,
Sorry, quickly.
yes,
What's n supposed to be? Like, what would you call n?
this is number of undecayed atoms. We can rewrite this formula for mass of undecayed. And that is where students get a little bit confused. Times 2 in negative t T on T, same thing.
What's the O in MO?
Initial.
Oh.
Initial. This is initial number of material. This is initial mass of material. And M is mass of undecayed material and number of undecayed atoms. Now, when I say mass of undecayed, does if you have some like sampled material, does its mass changes over the time?
Yeah. So I didn't
No. No, maybe like if alpha particle leaving maybe a little bit, but this is now mass of undecayed. If you have 100 grams of material, after one half-life we will have 50 grams undecayed. But other 50 grams still will be there, just decayed. It turn nucleus, turn into another nucleus. It's not disappearing. We always will have 100 grams of the same material. Just half of it will become not that it's decayed, turn into another chemical element. So mass overall does not change, but mass of specifically that material changes because half turn into something else. So let's consider we have 500 grams of 500 grams of strontium 90, which has a half-life of 28.1 years. T equal 28.1 years. Some elements decay very fast, in seconds, or even million microseconds. Some takes very long time. For example, uranium 238, and that's why in the periodic table uranium does not have a brackets around the atomic mass. Because it does, yes, it's decay, it's radioactive, but its period of half-life approximately equal age of the Earth, 4.5 billion years. So yes, it's decaying, but very, very slow.
So, like when you say it decays, does that mean like also physically? So like if you have something made out of
We yesterday, last lesson, we were looking into the uranium decay series.
Yeah.
So its decay turned into another chemical element.
So
And it ends up, uranium ends up through the uranium decay series. It turns out into what? What was the end of decay series that we were doing
it
last?
was, if it's alpha,
No, the end. We did long decay series. We did even competition on them. What
oh,
was
so it goes
Kelly?
into lead.
to the left after chain of decays. So that's what I mean. It's decays.
Oh,
Turn into different ones. But uranium, yeah, is decaying, but it's half uranium. To decay takes 4.5 billion years. That approximately like age of the Earth. Yes.
What makes some materials decay faster than others?
It's all determined by the balance of the forces in the nucleus, of the strong nuclear force and electrostatic repulsion. So how balanced or unbalanced they are determines how fast it will decay. If it is very unbalanced, it decays very fast. If it very close to balance, decay very slow. So question is that we have 500 grams of strontium 90. This is its period of half-life. Question is how long it will take to decay to 125 grams. How long it will take to decay from 500 to 125 grams. So what we need to do? We can do in two ways. We can solve this problem in two ways. First, divide 500 by 125 equals 4. So how many, yes?
It will be 4 times 20.
It will be 4 half-life, yes. All right, so That's we finding 500 divided by 125. We started with the 500, ends up with 125. So how many half-lives? 4. If one half-life is 28.1, 4 half-lives, 4 times 28.1.
Doesn't it like, wait, what? Doesn't it go from 500 to 250 and then 250?
Sorry,
Two and a half,
4.
2.5.
Yes,
So it's like
very good. It's not. It's 4 times smaller. So it becomes 4 times smaller. How many times it should decay?
Divide that by 2.
How many times we dividing by 2? Thank you.
Factor.
Thank you. Sounds at least someone following what we're talking about. This is 4. And 4 is 2 in which power?
2.
2. So we have from 500 divided by 2, we get 250. Then divide by 2 again, divide by 2 again, we get 125. So how many half-lives pass? 2.
Wait, but like why? Like how do you figure out something where you can't just write it down?
Oh, that's why you have the formula.
We know that after one half-life, amount of material half.
Yeah, yeah.
So 500 to get to 125, we need half. How many times?
No, I get that, but like what if it's a number that you just can't write it down, like going, like how would you put it in the formula?
Yeah, that's what I'm coming to this. So does this make sense? We found how many half-lives. Then we do 28.1 times 2 equal 56.2 years. That's how long it will take strontium-90 to get from 500 to 125 grams. If we now let's use formula. Let me use like common sense and basic logic. Let's use formula. We substitute numbers into the formula. We have,
What if it was like 500 grams to 300 grams?
okay, let's use first on this and then we will use formula when it's not dividing so nicely. So we have 125 equal 500 initial, 500 times 2 in the power negative, we're looking for time, unknown time, and period is 28.1. I've substituted numbers into the formula. Final mass 125 grams, initial 500, time that we're looking for, and period of half-life 28.1. Yes.
So it doesn't matter if the half-life is in like years or seconds, whatever, you still put it in the formula.
Yeah, we need to, the only thing that time and period of half-life has to be in same units. You cannot have one in years and another in days. They has to be in the same. How we, now, we divide both sides by 500. 125 divided by 500 equals 2 in negative t on 28.1. 125 divided by 500 is 1/4. 1/4 equals 2 in the power negative t on 28.1. 1/4 is 2 in which power?
2 to the power of negative 2.
2 in negative 2. So we have 2 in negative 2 equal 2 in negative t 28.1. So we have t over 28.1 equals 2, t equal 56.2. Now, this is numbers which divides nicely. But what if we have numbers that don't divide nicely? If we have, for example, this is not 125, we have 300. If we have 300 left. So we still divide 300 by 500, we get 0.6. equal 2 in negative t over 28.1. Then we need to use a logarithmic function. Then we need to use log. Need to use logarithm. We will have from here negative t on 28.1 will be equal log of 0.6 with the base 2. So t will be equal negative 28.1 times log of 2 with the base 2 of 0.6. That will box for any number. Now, the problem is that in the scientific calculator, CAS calculator has log with any base. So you can put it in CAS calculator and calculate the logarithm with any base. With scientific calculator, unfortunately, you have logs only with the base 10 or natural logarithm. You don't have, you cannot use any base log 2 in the scientific calculator. You don't have it. So what you can do on scientific calculator to solve such problem, on CAS it's very easy. On CAS calculator you have base of the log. You can use any base. You can choose base. For scientific calculator to find what this will be equal, what you need to put in the calculator, you need to put, so you do negative 28.1, you times, you have button ln, which is natural logarithm, on the green on the scientific calculator. You times by ln 0.6 and you divide by ln2.
What's ln?
ln means natural logarithm, it's logarithm with the base e. That for doing methods will, you have not learned about logs, exponential functions yet this year,
Not yet.
Yeah.
but you will learn soon, and you will learn about that number e. It's one of, like, often called Euler's number. It's one of those numbers like pi. Number e often coming in many like natural problems. So just you put this in your scientific calculator.
It's 20.7.
Hmm?
It's 20.7.
Three natural ones.
So you just wait, we just round it
So
up.
we have t equal negative 28.1
So we don't need that one.
log of the, yeah, what we got?
20.7.
So that will be 20.7 years. And that's logical, to get to 250, it needs to be 28 years. So to 300 grams, it will decay less than 28 and decay in 20.7 years. Yes.
Yeah. Right.
Okay, that's how we solve problems with the half-life. Like, subscribe and donate to help Ukraine fight Russian invasion.